teams that you will hear are teams that are part of a college pilot program. These are interdisciplinary teams involving other departments than ECE. This really is the first of a future thrust of the college to have more interdisciplinary work among all three departments, ECE, BME, and ME. As we all know, engineering and solving real live engineering problems typically involves integration from a variety of disciplines. So this year, for the first time, we have these two interdisciplinary teams involving ECE and biomedical engineering. The first such team is Team 2, Biosensation.
Today we'll be presenting on our project, Robust Immunosafe Platform for Resource Limited Settings. The motivation for this project stems from the need for robust medical technology in resource limited settings. Many of these resource limited settings are located in subtropical regions where mosquito-borne illnesses are common, such as malaria or dengue fever. As the map here shows, the red regions are regions that are least developed. And these regions happen to coincide with areas at the most risk for dengue contraction. So our project will focus on developing a robust biosensor to detect dengue fever.
So dengue fever is a mosquito-borne virus, meaning that's primarily transmitted to human patients through mosquito bite. The species of mosquito that carries dengue fever is primarily Aedes aegypti mosquito. There are 4 strains of dengue fever: D, E, and B, 1, 2, 3, and 4. And coming into contact with any one strain for the first time leads to primary infection. Primary infection is typically characterized by flu-like symptoms. Now, upon treatment and recovery of primary infection, your body is then immune to that specific strain you were infected with. The downside to this is, if you now come across any of the 3 remaining strains, this will lead to secondary infection, characterized by heightened expression of symptoms similar to primary infection. Also, you tend towards the possibility of getting a more serious disease, dengue hemorrhagic fever. Dengue hemorrhagic fever is characterized by patients going into shock, and if left untreated, they will eventually lose their life. Now, as Amy pointed out earlier, dengue fever is located in many underdeveloped nations, shown here in the orange on the map. These nations are also all subtropical or tropical areas of the world, where the mosquito Aedes aegypti that transmit the disease is most prevalent. The World Health Organization estimates that 3.6 billion people are at risk for dengue fever infection. And each year, 36 million people will report having gotten the disease. 2.1 million people will report with dengue hemorrhagic fever, and of those, 21,000 people will lose their lives. So once a patient sees an onset of symptoms, the virus is isolated in the body for the first 5 days. Upon day 5, the immune system kicks in and starts producing proteins to battle this disease, particularly IgM, or immunoglobulin M. Then again on day 8, another protein comes into the picture, immunoglobulin G, or IgG. Now, current lab tests currently test for those 2 proteins specifically. We're focused on capturing the virus in those first 5 days of infection.
As Chris mentioned, current diagnostic methods will only detect the antibodies. In addition to that, these diagnostic methods are costly to both purchase and maintain, require trained lab personnel, and a clean lab space, making these techniques inappropriate for research settings. Our goal, thus, is to develop a self-contained, compact, portable, and robust biosensor for dengue fever diagnosis using a technology developed here at Boston University called IRIS.
So as Amy mentioned, we're using this IRIS technology, and I'm going to attempt to explain what this is and how it works. So IRIS stands for Interferometric Reflectance Imaging Sensor. It's a label-free biosensor that we use to detect binding between antigens and antibodies, or even DNA to DNA. And it's able to measure nanometer scale height changes. So on the right, you can see a mock-up of a design. And if you direct your attention to the animation on the bottom, I'll explain how we can detect this binding. So imagine this is a ray of light hitting a silicon mirror. The ray reflects off the silicon, and its intensity is detected at the camera. So let's say we have a thin oxide layer. In addition, we also get a reflection off of this surface as well as from the silicon mirror. And at the camera, the intensity is detected, and these waves can potentially interfere constructively or destructively. So let's say we have antibodies on our surface. There will be an additional phase change that will result in an altered intensity profile at the camera. And we mix it with a patient sample, and if antigen binds to this, we see yet another additional phase change. And that is again detected as a change in intensity at the camera. So here we can see a cartoon of sample microarray. You can see that there are several different antibodies spotted, showing that we can test for different things, potentially each strain of the virus. And so what we do is we first spot the antibodies and we measure the height. Then a patient's serum is introduced. The sample is then washed to remove any unbound protein. And then the heights of the spot are measured again and compared to the initial measurement. Now, shown here is a sample image taken that we took with iris. You can see that there are 4 different conditions spotted. I think the first 2 columns is what we're looking to bind to, and you can see that it has a higher intensity, and that's indicative of binding. So previous iris designs used a tunable laser that scans from 762 to 786 nanometers, and it had like a 10 micron oxide layer, but the tunable laser is expensive and it has rotating parts, so not very cost efficient or robust. Currently in the lab, though, we have the illumination source has been changed to LEDs at various wavelengths in the visible range, and it uses a 500 nanometer oxide spacing layer to get this interference pattern shown on the bottom. And this is really the first step towards portability and cost effectiveness using this device.
So at the onset of this project, we aimed to develop a complete iris system and a portable interface. However, we soon realized that this was outside the scope of our project, so we simplified our approach to these 4 specific aims. The first of which was to deploy the LED control onto an isolated embedded system. Currently, the LED control is accomplished with the National Instruments Data Acquisition Device, requiring a firewire connection to the computer. The second goal was to simplify the optical setup, eliminating costly components while maintaining sensitivity. The third goal was to investigate preservation methods to preserve these spotted chips with antibodies, to allow for shipping and exchange in prolonged shelf life. The final goal was to develop a flow cell to maximize the binding interactions between the antibodies on the surface of the chip and the virus in solution. This is an image of, or a mock-up of our proposed solution, which would integrate all of the components of the device into a single interface, which would then be connected to a laptop. So first I'll describe the LED control system. The overall requirement here is that this system must integrate seamlessly with iris to replace the National Instruments data. Thus, the first specific requirement is that it must be able to be controlled via MATLAB, which is the programming language in which all of the processing and peripheral device controls are being implemented. The second requirement is that it must provide constant LED current, because variations in LED intensity can result in errors in our system. The third requirement is that it must be real-time, in keeping with this portability theme. So this slide shows the exterior of a mock-up that was developed to implement the LED control system. First, highlighted is the Genesis Photonics LED array, which contains the bare wafer LEDs which we use in our tests. These LEDs are each controlled by 4 separate 350 milliamp LED drivers, which are enabled individually by a mid-signal microcontroller from the MSP430 family. We selected this microcontroller for several reasons. First, because it has low power consumption. Second, because it has multiple serial ports, allowing for multiple add-ons and feature functionality. And also because of familiarity. So next is the Bluetooth transceiver. It shows Bluetooth communication between the LED control system and the computer for several reasons. First of which is that it eliminates a wired connection between the control system and the computer. And second, because the lab has been considering implementing iris processing on a smartphone. Most smartphones will have a Bluetooth connection, and thus if the LED control circuitry is controlled via a Bluetooth connection, the smartphone can easily control the LEDs. Also on this mock-up are system power knobs for both the most of the system and the LED arrays, and status indicators indicating whether the Bluetooth is idle or connected, and a battery pack for power. So future work in this realm is to take this prototype and design and fabricate a printed circuit board, and also to implement the imaging capability on a separate system, either on the embedded system or in a smartphone format.
Alright, so now I'm going to talk about the optical design, the LEDs, and the oxide thickness a bit. So before I was telling you about how previous designs had different oxide layers and wavelengths that they scan, we chose to use these blue LEDs that use the peak wavelengths shown, and the spectra are shown here. So some simulation work needed to be done to find the best oxide thickness to get the proper interference pattern. So shown on the bottom right is a graph of the a sample interference pattern that we would see at each of these wavelengths. Basically, we had to optimize it so that we get the highest accuracy possible in our fitting algorithm. And we found that 2 microns would be a good oxide thickness that would give this reflectivity curve, and it samples a full period of it. So you might ask, why are we using these blue LEDs? Well, because they're all a similar wavelength, we can eliminate the effects of chromatic aberration, and then we can move to a simpler optical design, where we can, instead of using a $700 objective, we can use a simple $70 lens. Or it can be even cheaper if we use less expensive optics. So just to walk you through the optical design, we use a 60mm and a 100mm focal length lenses in a simple 4F system. Then we use a beam splitter to combine the imaging and illumination paths, and an integrating sphere. So the LED light is coupled into this integrating sphere, which eliminates the spatial information and provides uniform illumination of the chip. So how do we collect our data? Well, we take 4 images of the microarray under each wavelength of illumination. The data sets are then fitted pixel by pixel to those reflectivity curves that I was talking about. Then the result from the fitting is a fitted image with a height in nanometers for each pixel. So images of the microarray, like I said, are taken before and after incubation with a sample, and then compared to see if there was binding. So just to walk through how we analyze our data, well, we developed a custom GUI for dengue diagnosis. And just to show you how it works, first the user loads a pre-image as shown. Then the user selects areas containing dengue antibody spots and control spots. The spot pixels are then identified via thresholding. The averages of the pixels are taken and standard deviations. Then a post image is loaded and the process is repeated. Then the GUI graphically displays the results of the test. These results will be shown a little later. And now Alex.
All right, guys, so on the biomedical side of things, we were really working on how to preserve those microarrays, which are basically one of the most important tools in our diagnostic test. And since we'd be eventually sending them to resource-limited settings, we'd have to be able to make sure that they could effectively capture our virus and be used for extended periods of time. So one of the first methods of preservation that we explored was lyophilization. And this is basically a simple process of freeze-drying the microarrays. So after we've prepared them, applying our proteins onto the surface, we've prepared 4 sugar solutions, placed our prepared microarrays in those sugar solutions, and freeze-dried them, removing all of the water from that solution, leaving the crystalline structure of the sugars to preserve the proteins on our microarray. After that, we inoculated using our serum sample to observe if there was still any biomass accumulation on those particular spots. And this is just the results that we've determined, and therefore that we could effectively use lyophilization as a preservation method for our microarrays. Now, as Chris and I were working on that, our electrical engineers were working on the actual hardware of the device, and once that was completed, we tested our device to determine if we could use it to detect that sort of binding. We set up a simple experiment using a protein and a control. Our protein is mouse IgG, and it's represented by the blue lines on the graph. The control is the red. We have pre-antigen, which is before we induced our viral sample, our post-antigen, which is after we induced our viral sample, and then the change in height of those particular spots on the microarrays. Now, as you can see, the blue showed the positive change in height, and therefore is indicative of a diagnostic result, and the control showed a negative change in height, which is usually due to some of those surface proteins on the microarrays washing off. So usually after that, we wanted to determine if we could actually capture the virus. So we set up 3 different dengue-specific probes. These are basically the antibodies that would bind to the virus in your body. We spotted those on the microarrays, and then we induced them with the viral sample. The probe 1 showed the best results, and therefore our most conclusive test to show that we could actually capture the virus. And then the last 2 probes didn't really show those results because we're still working on making that pairing between our antigen and our antibodies to develop our test. So we also, while we were doing these tests, we usually used a multi-purpose rotator in our lab to do our washes and our serum inoculations. But obviously, since it's about twice the size and twice the weight of our device, we can't be sending it to resource-limited settings. So we had to develop a better method to maximize the sort of interactions between our in-sample viral virus and our surface proteins. And that came in the form of a microfluidics channel. So this is just a simple design using a serpentine structure. Alone, however, is not good enough to induce or maximize the sort of interactions between our in-serum virus and our surface proteins. So we employed the use of this herringbone structure, which is basically chevrons that are etched into the ceiling of the microfluidics channel, which create helical flows. Basically the same way a bullet is rifled as it comes out of the barrel of a gun. So in the direction of flow is shown by the red arrows. And lastly, this gives you a better cross-section of the microfluidics channel with the 2 opposing helical flows and that herringbone structure on the ceiling. So that was basically what we used to maximize those sort of interactions and optimize our binding and therefore diagnostic results.
So in conclusion, we have accomplished our 4 aims by first simplifying and lowering the cost of the actual design, enhancing the mixing, which also requires fewer reagents, reducing the cost of running the test, proving the ability to detect dengue in solution, achieved a 6-week shelf life for antibodies and silicon chips, and developed a battery-controlled LED control system optimized for use by either a computer or smartphone. These modifications combined have furthered the work done to develop a complete, portable, robust virus system. We would like to acknowledge our customers, Dr. Salim Bundu and Dr. Mohamed Zaman, for their support and guidance, the graduate students from the Ultra Laboratory who were instrumental in the completion of these tasks, and the EC 464 instructors for their guidance as well, and our friends and family. Thank you.
So the probes we chose are dengue-specific antibodies, so they should only bind to the whole virus itself. Those have no proteins on the outside of the dengue virus specifically.
And all of our tests were done with purified samples, so we have not moved that to using actual human serum to do that. We're just using our purified samples, which are just the virus and just our probes. But that is a consideration to take into the future.
You very quickly described some little magic sphere that gave you uniform illumination. Could you just elaborate on that magic sphere a little bit?
Well, it's not really a magic sphere. Yeah, so it has like ports. It's like a 2-inch diameter sphere, and it has a reflective coating on the inside. So it also has a baffle so that the input doesn't go directly to the output. So basically, the LEDs are projected into in like a Lampertian pattern on the inside of the sphere, and it reflects, bounces all around a few times until the rays that find the output port exit. So it illuminates like the spatial information, because the LEDs are like a few millimeters apart. And so if we didn't have it, it would illuminate one side of the chip brighter than the other, depending on which LED was lit up. But because the spatial information is destroyed by the integrating sphere,
what do you mean by spatial information?
Like I said, like if you had one LED that was like a millimeter to the left, and you put that into our system without the integrating sphere, it would light up the left side of the chip more than the right side of the chip.
So you're getting a collimated, expanded light beam out of this thing?
Yeah, it emits sort of like inversion-like, but it's far enough away from the sample so that it's like collimated. Right.
Thank you.
showed on dengue fever versus the control indicates you need to be able to detect a height change of the order of maybe 1.5 nanometers. What is have you looked at the accuracy of your measurement system to determine whether or not you could actually reliably detect that height change?
Not sure how to answer that. Well, I mean, the iris system in the lab has probably like a noise floor in like the tens of picometers. So I would expect that ours would be a little higher, maybe the hundreds of picometers, but it still should have a sufficient resolution to detect 1.5 nanometers as opposed to.
But haven't you actually made measurements in the lab to be able to confirm that you could measure 1.5 nanometers?
Well, we ran a test during the semester where instead of using proteins, we etched like a 3 nanometer well into the oxide and measured that, and it came back conclusive that it was like 3 nanometers.